Welcome to a discussion of the Engineering Controls Operational Qualification and Process Pre-Qualification for the Biomet Aseptic Processing Facility. The Biomet Aseptic Processing Facility, located in Warsaw, Indiana, is a three-cell design consisting of a Class 100,000 outer gowning area, a Class 10,000 inner gowning area, and a Class 1,000 aseptic processing core, supporting a Class 100 critical work surface provided by a Class 2 Type B3 biological safety cabinet.
As the initial phase of the operational qualification, design velocities were verified at the aseptic core terminal filtration modules prior to validation of HEPA filter integrity in accordance with Sections 40 and 50, Federal Standard 209B, and ISO 209 specifications. Filter leak tightness was demonstrated by introduction of a polydispersed challenge aerosol directly into the supply plenum of each module. The entire downstream filtration media face was then scanned with an aerosol photometer to determine the percent penetration of the aerosol. All modules were certified for leak tightness in accordance with the standards. Following careful air balancing of the exhaust, supply, and downflow profiles, critical work surface downflow uniformity and velocities for the germ-free biological safety cabinet were established at an average of 78 linear feet per minute in accordance with manufacturer specifications. Upon certification of the downflow velocities, validation of the biosafety cabinet supply and exhaust HEPA filter integrity was carried out in accordance with Sections 40 and 50 of Federal Standard 209B and the National Sanitary Foundation Standard Number 49. Inflow air intrusion testing of the critical work surface was then carried out using a visual tracer. The gross inflow air parcel was observed to completely divert to the undertray return in accordance with design. The rear work surface recovery area was likewise observed to provide uniform clearance of the work surface to the rear undertray return. Clearance of the frontal recovery zone of the aseptic field was visualized and revealed no air intrusion over the work surface. Consistency of the supply downflow profile was then visually verified. Following the verification of proper cabinet airflow profiles, at-rest particle counting was conducted at the representative entrance plane of the laminar supply at a height of 12 inches above the work surface to assure Class 100 air quality at the critical work surface. At-rest certification of air quality at the entrance plane to Class 100 conditions was accomplished.
Following completion of the operational qualification phase, which demonstrated the proper operation of the engineering controls under at-rest conditions, process pre-qualification of the engineering controls was carried out during a simulated process pre-qual run. Aseptic processing personnel were provided with in-service training for the exercise, which was then performed to measure the in-process particulate contamination potential of the operative personnel. All operatives were gowned in accordance with procedures and were instructed to simulate actual processing operations without the presence of product.
Successful in-process particle counting of the aseptic processing core was carried out to verify operational Class 1000 air quality. Because the process incorporates a monomer which presents a potential inhalation hazard to operative personnel, visual tracer analysis of the operator's breathing zone was carried out to confirm engineering control of this potential hazard and to establish the uniformity and consistency of the unit inflow profile under operational conditions. In-process air intrusion testing of the work surface frontal recovery zone demonstrated uniform recovery of airflow from the work surface, with no air intrusion into the critical filling zone. Downflow profile integrity to the critical work surface was then demonstrated with processing equipment present on the work surface. The downflow profile was observed to produce a predictable smoke split at the work surface center, with uniform recovery of the tracer at the front and rear recovery zones. Tracer clearance of the operator's hands and processing equipment was carried out, demonstrating timely and uniform transit of the laminar downflow profile to and from the critical work surface. Finally, successful in-process particle counting of the aseptic work surface was carried out to confirm operational Class 100 conditions within the critical aseptic processing zone.
The operational qualification and process pre-qualification testing of the aseptic fill facility engineering controls demonstrates proper performance within specifications, thus providing effective support of the Biomet aseptic fill process.
Welcome to a discussion of the operational qualification for the Civco Medical Instruments' new East Process Clean Room, located in Kelowna, Iowa. Designed to provide ample space and complete flexibility in the rapid reconfiguration of its processing applications, this new Civco facility provides a 4,400 square foot, single zone, ISO Class 7 core and an ISO Class 8 gowning anteroom. Operational qualification of the facility was successfully carried out using 10 recommended tests of performance, as described in ISO Standard 14644-1 and -3. Test 1. Total airflow supply, recirculation, and makeup volumes. Test 2. Supply airflow velocity measurement. In Test 1, the total airflow supply for the core and anteroom was determined using a bolometer to capture and quantify the output of each terminal flow module, or TFM, at its face. Measurement of the total air recirculation and makeup volumes in CFM and LFPM was performed by a duct traverse of these ducts using a thermoanemometer. In Test 2, the supply airflow velocity for the non-unidirectional room TFMs was determined using an arithmetic calculation. The total airflow in cubic feet per minute for each TFM measured in Test 1 was corrected for the filter face dimension by dividing this value by the square of the filter surface, or flow aperture. to achieve a linear velocity value. All TFMs met the velocity performance specification. Test 3. Air pressure differential test. This test was successfully carried out using calibrated water manometers as primary standards for the measurement of pressure differentials between the core and anteroom and their pressure differentials to the surrounding area, with all doors and conveyor pass-throughs closed. Test 4. Installed filter leak test. All facility TFMs were tested for media and frame leakage in accordance with the standard. Testing was carried out by establishing an upstream concentration of polydispersed test aerosol in the upstream plenum of the TFM. The media and frame were then scanned to reveal any aerosol penetration in excess of log 0.5 on the logarithmic photometer used. Test 5. Airborne particle count for classification and test measurement of cleanrooms. Airborne particle counts were obtained for the cleanliness classification of the core and anteroom in accordance with the standard. Certification of these facilities in the as-built condition was achieved to ISO classes 7 and 8, respectively. Test 6, airflow visualization, and Test 7, airflow direction. Visualization and direction of the core airflow was accomplished using a smoke generator to verify the operation of each return duct and the direction of movement of the recovered air. Visualization of the return air indicated proper operation of the return ducts and the general direction of movement of this air to the return grills for recirculation through the HVAC system. Test 8. Containment leak test. Containment leakage testing of the facility was carried out to detect the intrusion of air and contaminants into the core and anteroom facilities. Using a gross smoke generator, successful testing of the core entrance, anteroom entrance, conveyor pass-throughs, and emergency exit door was carried out. No contaminant intrusion was detected at these entry and exit points to the cleanroom facility. Test 9, recovery test. A recovery test of the facility core was carried out to establish the ability of the installation to eliminate airborne particulates and to return to a state of equilibrium. The stringency of this test was increased by 1 order of magnitude over the ISO requirement of a 100-to-1 reduction to a 1,000-to-1 reduction to an equilibrium state. A Class 9 level of particulate contamination of the north third of the core as a return ventilation worst-case location was created using a gross smoke generator. Following equilibration of the particulate levels within the room, rapidly sequenced particle counts were then taken within this area to determine the point at which the facility experienced the desired 3 order of magnitude reduction of this contamination level, returning to its as-built cleanliness classification of ISO Class 7. A 3 order of magnitude reduction was achieved in less than 4 minutes, with a 5 order of magnitude reduction occurring within 6 minutes, thus exceeding the requirements of the standard. Test 10, temperature test. In order to demonstrate the ability of the HVAC system to maintain the specified air temperature level within the control limits of the core and anteroom facility, the internal facility temperature was measured continuously for a period of 2 hours. The Civco process cleanroom core and anteroom demonstrated less than a 2 degree centigrade variation over the test period, indicating adequate ability of the system to maintain the desired internal operating temperature during the period of the test. The successful performance of the 10 testing procedures recommended in the ISO standard indicates successful completion of the operational qualification of the Civco new East Cleanroom facility.